In this video, I will be going over the section 6.1 Day 1 notes. This is our first section in chapter 6, and we are starting with domain and range, which we have talked about previously. But as a reminder, the domain of a function is the set of all x values that are represented for that function. And basically, it's all of the input values that you put in. And so the range then represents the set of all y values that are corresponding to those x values, and they are the outputs of the function. So if I put an x value of 3 in, and then I get back a value of 7, those are each an element of the domain and the range. And so for right here, it's just a reminder that when you state the domain and range of a relation, that the elements in the domain and the range are always listed from least to greatest. And so we talked about relations back in chapter 2, but a function is a special type of relation that we'll get back to. But when you want to list out the domain and range of a relation, you list out all the x values from least to greatest. And you list out for the range all the y values from least to greatest. And if there is any repetition in those values, then you just list it once. You don't have to repeat it in the domain and the range. But you'll notice I did go in increasing order. I went from least to greatest. And that's going to be the way that we write the domain and the range even for functions themselves. And so it says in the following 6 problems to identify the domain and the range by using the graph. So this is a little bit different, where you're going to have to use the x-axis to help you identify the domain, because the domain is the set of all x values. And then for the range, you're going to have to use the y-axis. So in order to visualize this, I'm going to highlight parts of this problem. I'll kind of start with pink here for the domain. So the domain is the set of all x values that are being represented for this graph, and hopefully you can see that this graph starts over here at this endpoint and then travels to the right, and when it lines up with that open point, it's going to stop. So I want the domain to be all of the x values that are represented by that highlighted line. So the way that I would write this is going to be a compound inequality. So I'm going to start over here. This would be -7. And the way that I'm going to write this compound inequality, since I'm going from least to greatest, I'm going to use the less than or equal to sign. Now x is going to be all the values between -7 and whatever this value right here is. So 1, 2, 3, 4, 5. Now I'm just going to use the less than symbol here because it is an open point, so I don't want to include 5 as part of the domain. I just want to go up to 5. And the last thing I'm going to do is put this in curly brackets. And that's how I can write the domain for this problem. The range, now I'm just going to use the y-axis, so I'm going to start at the lowest point because I want to go from least to greatest. So the lowest point's actually going to be down here, and it's going to go up to hit that and line up with the open circle. So the range here is going to be a lot smaller than the domain. So I line up down here with this closed point. This is at -3. Is less than or equal to y, is less than, and then it just goes up to +1. Another way that you can think about this, if you're having trouble visualizing where these numbers are coming from, this point right here is the point 5, 1, and this point right here is the point -7, -3. So you can pick off, you'll notice that the domain goes from the x value of -7 to the x value of 5, which is what I listed here. And then the range goes from -3 to +1, which is what I've listed here. And I'm just stuck between those values. But I don't always have to be stuck between values. I can have things look a little bit different here. So if I go over to problem number 2, the domain starts at the origin and it goes on forever towards the right. So this is not a compound inequality, this is a single inequality, and I would say that x is, since it's going to the right, greater than or equal to, and then the x value represented here right at the origin is 0. But the range is a little bit different. The graph goes up, and there's an arrow there, so you assume that it's going to go up forever. But the graph also goes down, and it's going to go down forever. So I've highlighted the whole y-axis, so the way that I write that would be y is any real number. Number 3, the domain is going to be stuck between these two endpoints right here. And those are the only x values that are being used. So this is a compound inequality since I'm using two different endpoints. So this would be -4 is less than or equal to x, which is less than or equal to 4. I used closed circles here because there's no open circles on the graph. So then I use the or equal to symbol. And then the range is going to be similar because it's a circle. So same thing for the range, it's just we're using the blue part for this part. All right, so with that, let's keep going here. Number 4, my domain. You'll notice I do have some open points here. My domain is going to be in between these 2 points. And so I want those to be open circles, or at least I don't want to put the or equal to symbol on these inequalities. So it almost looks like it's symmetric, but it actually goes -3 is less than x, which is less than 4. Slightly off, it's slightly longer on this side. And then the range is going to start at the origin and just go up. So it's just that part right there. And the way that I'd write that would be 0 is less than or equal to y, which is less than 5. So once again, you could write out the points if you wanted to, but a lot of times if you can just look at the x or the y-axis, you don't have to show any extra work. But problem number 5 is kind of the one that doesn't have any endpoints to deal with, so it almost looks like it's going to be tough to write this out, but the domain literally is any real number because it goes forever to the left and forever to the right. And same thing with the range. It goes up and the graph goes down. So this is a line, and any line has a domain and range of any real number. And the last one is a parabola. So we've talked about these before. A parabola will always have a domain of any real number because it goes to the left and it goes to the right. But the graph does not go down at all, so the domain is restricted to be y is greater than or equal to 0. So some examples for you here about using a graph to find the domain and range. And so now we're going to flip over to the back. On the back, a quick review of some definitions here. A function is a relation in which each input has only one output. And so basically, if you were giving a set of points, you're looking at the x values. Okay, so if I highlight this 4 here and this 4 here, the reason why this is not a function is because 4 can correspond to 2 different outputs. Okay, so if you look here, 4 not only corresponds to this y value of 5, but it also corresponds to y value of -1. So it says why or why not, and you could say it has more than one output. And I've kind of shown those two outputs here. But I'll go ahead and let you fill in the explanation. The vertical line test can be used to determine whether or not a graph represents a function. So instead of me giving you a set of points and asking you if it's a function or not, what if I give you a graph instead? So the vertical line statement is this. If a vertical line passes through a graph of a relation at more than one point, then it is not a function. And it says, go back to the front and see which graphs are not functions. So if I pull my paper out from before and just do a quick look, if I use the vertical line test, 2 of these are going to fail the vertical line test. And if you look really carefully here, it's going to be number 2 and number 3. Because if I put a vertical line right here, it will touch this graph in more than one location and through the circle as well. Now you could draw it where it only touches it in one point, but the vertical line test, you're imagining that you draw multiple vertical lines, and if one of them touches the graph more than once, then it's overall not a function. So the rest of them would be safe, and they would pass the vertical line test, but number 2 and number 3 would fail the vertical line test, and the explanation there would be the vertical line passes the graph in more than one point. But probably the most important part for today is going to be this bottom part. Okay, so we kind of saved the best for last here, and I can't stress how important the next few problems are going to be, because you've probably learned everything up to this point previously. This part here might be new for some of you. Finding the domain of an actual function. So we've been talking about points, we've been talking about graphs, but what if I actually list out a function without a visual? I want to find the domain of these functions. We're going to ignore the range for right now and just focus on the domain. But the 2 big things that we're going to look at today is how do we find the domain of a rational function, aka a fraction, and then how do we find the domain of a function involving square roots. And they each have their own rule. So when you have a rational function or a fraction, the denominator can never be 0 because you can't divide by 0, it's undefined. So when I want to find the domain of a rational function, it doesn't really matter what's in the numerator, because we want to focus on the denominator not being equal to 0. So for number 1, you're just going to take whatever the denominator is, and you're going to say it can't equal 0. So if I solve that for x, that would imply that x cannot be -5. And so what this means is if I plug -5 back into this function, -5 plus 5 would be 0. That would give me 4 over 0, and I can't have 4 divided by 0 because it's undefined. So -5 is not part of my domain. This is called a restriction on the domain. So what I'm implying here is that the domain can be anything but -5. It's the only value that we can't have here. So if we think of the same type of process for number 2, I would say that the denominator cannot be equal to 0. And here I'm just going to have to do some factoring in order to solve this. So factors of 24 that I'm going to want here are 6 and 4. And so in this particular problem, I get 2 different restrictions for the domain. So the domain can be anything but 6 or -4. So if you plug either of those functions into the denominator, if you plug either of those values into the denominator, you'll get the 0 in the denominator just like we did in problem number 1. So a lot of times when you write out the domain, you write out the domain like we did on the front side. So, using inequalities or maybe any real number, something along those lines. But here on these two problems, we actually listed what we can't use. So there's two different ways to list out the domain. It seems to be a little bit easier on these two problems to list out what we can't use because we just have a couple restrictions. And so the last part here is finding the domain involving square roots. The radicand, that's the term underneath the root. It always has to be greater than or equal to 0. Otherwise, you'll get an imaginary answer. Okay, so I don't want the radicand to be negative. I don't want to take the square root of a negative number. So whatever is underneath the square root, you can ignore everything else. Whatever is underneath the square root, you're just going to say that it's going to be greater than or equal to 0. And then you're going to solve for x. Now you'll notice that if I put this in curly brackets, we get an answer that looks similar to what we did on the front of the notes today. So here we're writing it in the traditional notation. For number 4, it would be 4 minus 3x is greater than or equal to 0, and then you would solve that for x. Let me show my work here because I was going to write the final answer, but I want to remind you, if I show my work here, that when you subtract the 4 and then divide by -3, when you multiply or divide by negative, it flips the inequality. So you probably just saw me writing the final answer where the inequality was flipped. And the reason why I'm flipping the inequality is because I divided by a negative number. So I was just going to write that final answer, but I did want to remind you of that rule. Now this last one is a little bit different because the term underneath the square root involves factoring. So this is something that we've touched on previously, but I want to really go over this problem. So x squared minus 2x minus 15 has to be greater than or equal to 0 since this is the part underneath the square root. And you probably guessed that we're going to have to factor here. And so this would be x minus 5 and x plus 3. That doesn't mean I have two restrictions like I did in the previous problems 1 and 2. This is actually a little bit different because these two values right here, 5 and -3, are boundary marks on a number line. And we did this when we graphed parabolas, though we didn't spend a lot of time on it. So whenever you have a squared term underneath a square root, I would just solve it like usual, but when you get to your answers, put them on a number line from least to greatest. I'm going to use closed circles for this number line because I have this or equal to symbol. And basically, you're going to figure out where to shade. And you're either going to shade in between these two numbers or on the outside of the numbers. And this is what we saw previously when we were graphing inequalities with parabolas, because essentially this right here is a parabola. But there's a better way to do it than looking at the graph. And so the easiest way to determine where to shade is to actually test a number. So what I'm going to do, and I'm going to use 0 because it's the easiest number to test, I'm going to plug 0 into the starred statement. So that would be 0 squared minus 2 times 0 minus 15, which is just -15 is greater than or equal to 0. So here's how the test works. 0 is probably like right here on my graph. Is this a true or a false statement? If this is a true statement, then I would shade inside or in between these two numbers because that's where 0 is located. If this is a false statement, then I don't shade where 0 is. I shade on the outsides. And you'll notice that this is a false statement. So then I would shade here and here. It's a much faster way than using the graph of the parabola. I will note though, let's say that 0 is actually over here, right? So if 0 moves to not be in between them, and if it was true, then you would still shade out here, but if it was false, then you'd go back inside. So it depends on where this number is on your number line, so make sure to graph it correctly. By the way, the way that I write this answer would be x is less than or equal to -3, or x is greater than or equal to 5. And we've written answers like this before because we've solved these problems before with the graphs of parabola. But more on this particular problem later. And that's the end of your video.